We have three scientific and three statistical hypotheses. The first one of the scientific is that the blast force per time affects phosphorus contamination, and its statistical hypothesis is that the means of phosphorus contamination of each blast furnace per time are equal. The null hypothesis is that the mean of time equal to is equal to the mean of phosphorus contamination of time equal to 4. And the alternative hypothesis is that they are not equal. The second scientific hypothesis is that the temperature variable zone of arrival to each zone affects phosphorus contamination, and the statistical is that the means of phosphorus contamination of each temperature of arrival zone 2 are equal. The null hypothesis is that the two means of phosphorus contamination of the two different temperatures 2000 and 2500 are equal, and the alternative hypothesis is that they are not equal. The third scientific hypothesis is that the air feed speed affects phosphorus contamination, and the statistical hypothesis of this scientific is that the means of phosphorus contamination of each air feed speed are equal. The null hypothesis is that the mean of phosphorus contamination of air feed speed of 120 is equal to the mean of phosphorus contamination of air feed speed of 150, and the alternative hypothesis is that they are not equal.
In order for us to define our best distribution, we need to know some things about our data. The first thing is that our variables are continuous, so we need to choose a continuous distribution. The second thing that we did in order for us to define our distribution is that we use some functions in R. The function of fit dist that makes some distribution tests, and the results are the following. Our decision is based mainly on the log likelihood result, and we choose the one that is the highest, but we also choose the distribution according to how the fit dist arrange our distributions. So for speed, we have that the highest is the normal distribution in the case of 120, but in the case of 150, we have that the normal distribution is one of the highest, but not the highest, and we have that variable distribution is the highest. But in this case, the fit dist function arranged it so that the normal is the highest, according to the other distribution tests.
Here we can see the respective QQ plots for 120 and for 150 air feed speed, and we can see that they behave linearly. This is our other criteria to select normal distribution for these variables and these parameters.
For temperature, we have a similar result. In 2000, we have that the normal distribution is the highest, but in 2500, we have that the normal distribution is one of the highest, but not the highest. We have logistic as the highest and variable as the next one. But nevertheless, the result of the normal distribution is very close. And as for the other case, we had that the software arranged it so that the other tests are giving it more weight, so it comes on top.
Here we can see the QQ plots that for 2000 and 2500 degrees for temperature of variable to zone 2, and we can see also a linear behavior that tells us that they behave also normal, and we can select for this also normal distribution.
For purge time, we have that for 2, the normal distribution also comes at the top, but we have that the gamma and beta distribution are higher, but just for 0.07, and that the normal has the same value as the log normal. But as we said, the difference is minimum. For push time equals 4, we have that the normal is not the highest again compared to the variable, but it's one of the highest. And the fittest function also puts normal on top.
Here we can see also that the two samples behave linearly in a normal QQ plot, so we can infer that the variables have a normal distribution.
Looking for outliers, we made box plots for all of our data, finding that for air feeding speed equals 150, we have one outlier, and by removing it, we see that our data fits better the normal distribution, seeing that the QQ plot is better fitted and that the log likelihood test gives normal as the highest number. The same thing happens with temperature equals to 250, and we see that we also have one outlier, and by removing it we see that the QQ plot fits better the normal distribution and that the log likelihood gives normal and beta as the highest with 104.57, and still the normal is on top of the list.
For exponential family, we selected normal distribution. We apply log to sigma and expand the quadratic formula. Then we applied log to sigma to eliminate the -1 exponential. Then grouping the variables can help us to select the parts of the canonical form, like h of x, g of the parameter, t of x, and a of the parameter. Then we assign the canonical form for eta 1 and eta 2, and eta 1 is -1 over 2 sigma squared, and sigma squared is equal to -1 over 2 eta 1, and eta 2 is mu over sigma squared, and also mu is equal to eta 2 times sigma squared, and this can be rewritten as minus eta squared over 2 eta 1. Then for a of the parameter, the formula a of the parameter we have for a eta, that is minus eta 2 over 2 eta 1 to the power 2 times eta 1 plus 1/2 of the logarithm of -1 over 2 eta 1. And all of this can be transcribed, rewritten as minus eta 2 power 2 over 4 eta 1 minus 1/2 of the logarithm of -2 plus 1/2 of the logarithm of eta 1. Then for the expected value of t of x squared, we have that is the partial derivative of eta 1 of the formula of a of eta 1. And we have that the result of this derivative is eta 2 squared over 4 eta 1 squared plus 1/2 of eta 1 can be transcribed or rewritten as eta 2 over 4 eta 1 to the power 2 minus 1 over 2 eta 1, and this can be rewritten as mu squared plus sigma squared. And for the expected value of tx, we have that the partial derivative of eta 2 of a of eta 2 can be written as -2 eta 2 over 4 eta 1, and this simplified is minus eta 2 over 2 eta 1, that is also written as mu, and we can see here in the canonical form. And the variance of tx squared is the second partial derivative of eta 1 with respect of eta 1, sorry, of the formula a of eta 1. And the result of this second derivative is minus eta 2 squared over 2 eta 1 to the cubic plus 1/2 1 over 2 eta 1 squared. And the variance of t of x is the second partial derivative with respect of eta 2 of the formula a of eta 2, that is minus 1 over 2 eta 1, and this is equal to sigma squared, also the variance. With these values, we can confirm that our procedure is correct. For CRLV, we use the normal distribution also. We know that that there is a product in this part of the density function, so we apply a summation of the logarithms to eliminate this product. Then we apply the log likelihood to the density function, and we do all the procedure to obtain the following formula, that is minus n over 2 times the logarithm of 2 pi minus n over 2 the logarithm of sigma squared plus the summation of xi squared over 2 sigma squared plus the summation of xi times mu over sigma squared minus mu squared times n over 2 sigma squared. With this formula, we can work with it to obtain the score functions. With partial derivative, the partial derivative of this function in respect to mu, and the partial derivative of this function with respect of sigma. And we obtain that the partial derivative with respect of mu at the end is the summation of xi over sigma squared minus mu times n over sigma squared. And the partial derivative with respect of sigma at the end is minus n over sigma plus the summation of each xi element minus mu to the square over sigma square. Then if we compare that to 0, we equal that the score functions to 0, we can obtain the following answer, that mu is the summation of each element over n, and the one that respect of sigma is that the sigma square is the summation of each element minus mu to the power 2 over n. And these are the formulas that we can use and we can found in books for the mean and for the variance in a normal distribution. Then to obtain the variance of a expected value, we know that the variance of a expected value is greater or equal to 1 over the feature of a parameter. We selected the parameter that in our case is mu, because we are working with means, is 1 over minus the expected value of mu, and this is 1 over minus the second derivative. Here we have it. This comes from here. The second derivative with respect of mu is minus n over sigma squared, and here is 1 over minus n over sigma squared, and this gives us sigma squared over n, and this is the variance of our mean. Thank you for your attention.